Let's see. See where things are. All right. Things are. Well, verified the sound works. Let's see. It's all well and lovely over there. Let's see. Well, there's definitely sound on Twitch. Well, there's definitely sound on Twitch. All right. Let's try. Don't need that. Don't need that for now. YouTube test. YouTube test. YouTube test. YouTube test. At the oddest circular sound or something. What is the oddest circular sound or something? What is the oddest circular sound or something? What is oddest circular sound? What is oddest circular sound? Hmm. 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 So I don't know why the sound is circling around back and forth. That's really odd. So I don't know why the sound is circling around back and forth. That's really odd. I don't know why the sound is circling around back and forth. That's really odd. All right. So there should be only one place for audio now. All right. So there should be only one place for audio now. All right. So there should be only one place for audio now. So there should be only one place for audio now. What the hell? The hell? The hell? Okay. 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 All right. I can no longer hear myself. But maybe we won't have that echo. Anyway, sound is what it is. All right. Let's see. Feel free to comment and stuff. We won't have much interesting going on background music wise. Oh, I know what I can do. Let's try this. If I go over to here, I'm not using any of the sound. So the sound is being captured by StreamYard, and my virtual camera is doing the rest. All right, well, we'll just go with it. Whatever. All right. So let's see. We've got our little boot monitor. Oh, lovely. That's it running. Do a command. We get our memory command. See how that memory command would work. Memory read and address 0. And sure enough, there's the command at address 0 that we just typed in. So that's as far as we've gotten at this point. What we have, if we do memory read and we do some other address, doesn't work. Same. Oh, that's interesting. I didn't print carriage return at the end of that. That's weird. Look at it, it's even at 10 for some reason. see, memory read. How is this thing just automatically incrementing for me? What is that about? Why are you doing that? I'm just incrementing by 10 each time. Go figure. All right. So if we come down in here to memory halt, this is where we're setting up the lines. Dump lines is set up to 1. And I guess I'm just never setting the address back to 0. Because, yeah, we are destroying our util functions. Dump start. Dump start is the address we are looking for. And we should probably do this over here. And inside our memory function, what we really want to do is convert the 1, 2, 3, 4 into the address we want to print from. But for now, just so that we get the same behavior, set it up as 0. So we load the value dump start into the DR register. And load 0 into A. Store in direct A. And put 0 in there. And then we increment the DR pointer to the next one. And whoops. Do it again. So let's walk through that. We'll put a halt and a no-op. And that's my breakpoint so that I can see what is going on. So exit that, make sure we've saved the file, compile it, run the simulation, let the simulation run, MR 1, 2, 3, 4. All right, there's our halt. Not so single step. So we're going to load the address dump start into the DR register. There it is. Apparently it's 44. And we're going to load A with 0, which is already 0, so we don't really see a change. We store that. If you look at 44, here's where we're actually writing. Now we increment the DR pointer. Now we're looking at this address, and it's 0. Of course it's 0, because it's the first time through. Now if we run from here, sure enough, we're dumping at 0. Should probably turn on the mouse thingy. Where are you, little mouse thingy? That's not the right one. Wrong program. There's the right program. Now we got some highlighting. So these is the address. And of course, it was 0 to start with. So let's try this again. MR 1, 2, 3, 4. We halt. Load the address of dump start into DR, which is 44. And there, sure enough, there's the one that we wanted blank or set back to 0. And 0 into A, store A into there. Sure enough, increment DR once again, store 0 in that address, and then continue. So there we go. All right, so we fixed that problem. Now what we need to do is create this hex to short, if you will. Convert those 4 hex characters into a 2-byte value. So to do that, to call that function, we're going to push 2 values onto the stack. A pointer to the start of the string we care about, and a pointer to where we want to put the result. Then we're going to call the function. Then we're going to delete those off the stack. And if A is anything other than 0, then the conversion worked. So let's see. We need to push the pointer to the start of the string. And the pointer to the start of the string is command string length, or command string rather. Command string. So load that address. It's not the first character in the command string or the second, it's the third character, third, fourth, fifth, and sixth characters. So load that. Then we're going to load a value into the T register of 3. For x03 to be exact. Spare that. So we load the address command string. We load 3 into T. And then we're going to sum. Well, that's minus. We want to sum, which is over here. This is the sums. These are the minuses, the sums, the shifting commands. So we're going to sum into D whatever's into T. So this will add T to D and put the result into DR. I say D, DR. And now we have to push that value onto the stack. And so we want to store onto the stack the value in DR, but we need to do it in little endian. So we're going to push R and then D. So store stack related D and R. So SCR and SCD. If I did that right, we should have pushed those values onto the stack. And now we need a location to come back from rather. And where do we want to put it? Let's see. What do we want to do? I create another variable. Well, it really only needs to be a temp variable. And actually, take that back. This is where it needs to be put in. Brr. So we push that on the stack. Now we want to push start. And we don't need to add to it. We just need to store that location on the stack. Then we want to call our function, which we have yet to create. So where do we want to create this function? Let's see, detail functions. That's where all this is. So let's see, where is it? Divide. Oh, here we go. So this function already did all the checking, put a value in the B register, call this function. It'll tell you whether or not that value is within the typical characters for hexadecimal 0 through 9 and A through F. And if I remember right, it only checks for uppercase. Yeah. All right. So since we're going to be calling that function, we can probably put it somewhere around here. Oh. X, the string of X refers to be on the stack. So we're going to make a constant. It's going to be oops. First off, let's just define the function xtos. And we're going to create some constant xtos dot. What do we want to call it? String. And that is going to be a value of, so 2 bytes. So there's the return values on the stack. And -2 or +2 on the stack would give us the second thing passed. And +4 would give us the string. So the string and the value, sure, why not? That's 2 bytes on the stack. So SP +4 equals pointer to our string, and SP p plus 2 pointer to our value. All right, so what do we want to do? Because we're doing everything in Little Indian, we need to, the string is in Big Indian, the values are in Little Indian, so it might actually be easier to do the second and thirds. So let's just put a little note in here. So the string's in Big Indian like 0x, big number, smaller number. Let's just do it like this, 1, 2, 3, 4, right? Maybe even more interestingly, ABCD is stored CDAB. Little Indian. So the first thing we want to do is take a look at the, well, just for debug purposes, let's put in our debug commands, halt processor, do nothing, and that skips over it. So just put a comment here. Breakpoint. So our string pointer to string equals, I guess I should dereference that pointer to string, right? Oh, come on. Equals. So the first thing we want to do is read C and D. So we're going to look at, to see, we need to first get to that character. We need to first get the stack pointer with the data pointer, or rather, so this one. So pretty much put into the DR register the contents of the SK register or stack. So PDS. That copies stack to the register. Then we want to add that value, so we're going to ltextos.str and edt. So this loads into the T register from EEPROM, and the EEPROM value it's going to stick is that, which is 4. So that's 4. And that. Now we want to get from this one, from the A, over to the C. So we're pointing at A, we need to add 1 and 2 to get to the C. So let's add another 2. And we can do that with LTE2 and EDT again. Now, our DR pointer should be pointing to 8. No. Well, that points to the value. Now we need to read that value into A and B. So we need to LAM load into A from memory that is being pointed to by the DR register. Remember, we're passing a pointer on the stack. So we have to sort of dereference it twice, if you will. So load into A from memory. At that point, we need to increment the DR register and load into B the next value. All right, so now we have those values. Now we need to put those values back into the DR register so that now the DR register will have the pointer to the string we're interested in, which would be simple LBR and LAD. So copy the state pointer into the data register. SP offset. Add offset. DR. Oh, I don't want to do that yet. No, I did. This is the add offset, rather. Load into A. The value pointed to by DR. That's going to be the littler part of the value, the significant bits part. So A is what's going to have to go into R. And B is going to go into D. And offset. Right here. I should say, let's see, this would be load LSB Okay. And we load command to be. Well, we take load R with must be D must be. All right. So all of these commands are part of getting the value off the stack that we passed earlier. And let's see. Let's just make sure all that works first. We don't need this for now. Let's just halt here. And I suppose I should have a return value since this is a function call. Right. So that should be all we need to get the value where we expect it. Let's see, now we got this. This is going to be no fun because dump start is at 0. We need to put dump start at something more interesting. Where is dump start defined? That's what the map file is for. Let's see. No, values command string. Okay, so dump start is at 0044. Let's make that at least something bigger. The dump start is going to be in util functions, I think. Let's see, where did I put it? This is probably in the map file of util functions. Util functions map. Oh, not map file. Ooh, symbol table. See, like this, there's the symbol table. That's the symbol table for the whole program. There should be a symbol table for each individual one. It might just be easier to find all the places where dump start is located. Not very useful. Oh, in current document and all open documents. There we go. Here's our definition of the variable dump start. And just before this, we can do a capital A, and that'll set the start address. So if we do that, we should move the variables off to 0144. So let's see how that works. Compile. Nobody complained. That's a bonus. And let's go back over to the map file. Well, lovely. Let's see. Maybe we want to start it at 0, 1, 2, 3. Or 0, yeah, 0, 1, 2, 3. Let's do that. Start. Oh, where were you? Zero, 1, 2, 3. That'll make it easy to notice. Maybe we make it even easier. 0, A, B, C. No. No, that'll be easier. Easier to say. Can I start at A, B, C, D? Sure. I can do anything. And that'll make it easy to see, easier to see the effect of everything and the Indianness and so forth. There we go. Now dump start is at ABCD. And ABCF is dump lines. Yeah, it's taking up a bunch of excess memory, but whatever. Alright, so that works. In the memory function, would help if we actually called the function, right? So now we're going to call the function after we push dump start. So let us change our breakpoint. Let's comment this so we know why we had this here. Dump start to 0. All right. Load 0, store it, increment, store it. Now going to let's put the breakpoint here. Halt up breakpoint. Pair. And then F10 to compile. F7 to run. F5 to keep running. And now let's type in MR 4321. All right. So now we hit our no op. All right. We can F10 single step through our emulation. We're going to load into DR the value of command string, which is 0. Now we're going to load 3 into T. Sum those up. Gets us to the start of that. Now we want to store, and it won't be easy to see because our RAM, we don't normally look at the stack area. I mean, I guess I can look at the stack area. We'll do this command individual micro step at a time. So one micro step at a time. We're going to store based off of the stack pointer, the value that's R, and our stack pointer is FFFD. So if we do this single step at a time, well, that's annoying. Must have been F9. There we go. what we're doing is we're going through each individual sequence in the microcode now to where we can get to where we can see the stack pointer. So there's our function call return pointer there. Here's where our stack pointer is currently pointing at. We moved over this 0 from D. Should have stored R, not D. Oh, there it is. There's the actual store. So we copied the R of DR into that point in our stack. And we're going to decrement our stack. There we go. And we just decrement the stack pointer again. Now we're looking at the stack pointer value. We're going to take D, which is 0, and put it over there, which is kind of boring because 0 is 0. All right. So now we loaded dump start, ABCD, into here. Let's see, dump start is ABCD. So we took dump start, put it in ABCD, right? And we stored R, which, since we're not single stepping, you don't see it, but let's single step from store D. I should say micro step. Now we're going to take one more micro step. There's our ABCD on the stack. Now we're going to call xtoss. There we go. We hit our breakpoint again. Now let's see if our setup is correct here. Let's take our... This should copy the stack pointer to the data register. So there's our data register, there's our stack pointer. Row. That did not do what I thought it would do. That's annoying. You seem to have rebootified. Nothing like a total reboot, eh? You double check. I don't think that command is right. Exit emulation. Let's see, util functions, PDS. All right, did I use the wrong? Okay, let's get our document here. Where did we go? Always fun when you have to reference your own documentation, huh? So this is all the gory details of the setup and everything. Some examples of stuff written before I had an assembler. And here we go. We need the pointer copy functions, PSD and PS copy size from the DR high-low into the SP high-low. That's PSD and PDS. PDO copy. I was supposed to add A. PSD and PDS copies the value of the DR to SP or the stack pointer to the DR. So PDS should work. All right. Where do we get the breakpoint set there? So let's try this again, but skip that upper level breakpoint. Rebuild. Rerun. So we just run MR 1, 2, 3, 4. There's our breakpoint. And PDS is just supposed to copy this to there. And it reboots. So let me check. Did I use this already? PDS. Oh. POE. POE is supposed to be copies the stack pointer, adds the next byte. Well, that would be a convenient one, right? Yeah. Maybe this is a command I haven't actually implemented. Oops. Not all assembly language instructions are completely implemented at the moment. Now let's try PO. PO looks more interesting and more useful anyway. So in util functions. Yeah, because PO gets rid of all three of these commands, puts them into one. And now that I vaguely remember, I probably did this because it was more useful, right? So instead of those three lines, POE xtos.str. There, that's what I should do. That should take the stack pointer, put it into the stack pointer, put it into the data register, and add that value. All right, save. Oops. So this is a problem with short jumps. Util function is line 430. Util function is line 430. We have a function that has crossed the Rubicon. Call repeat character. Oh, yes. Got to compile from your main file. There you go. Always fun, huh? There we go. And F5 to run. Memory read 1, 2, 3, 4. Sure enough, we hit our breakpoint. Now this should take FFF7, put it in here, and add 4 to it. So that will be FFF 8, 9, 10, 11, FFFB. See how it goes. Doop. Hey, that worked. There's FFFB. So now FFFB points to, is that right? Need the 2 for the return address, the 2 for the pointer to the string, and then the 2 for that. Seem right? I think I might have that backwards. If we move the LSB in there, sure enough, we increment the data pointer, and now we're looking at the wrong space. So is it 2? Probably need to decrement the data pointer instead. But shouldn't that be further up? Because here, before we call the function, so when we call xtos, we keep the address of the next instruction. That's the first thing we put on the stack, or the next thing we put on the stack. So the very first variable that gets pushed on the stack is at least 2 away. And this one should be 4 away. Looks like we just got an off by 1 error going on. So, off by 1 error. Go about dealing with that. Why does it seem like I'm off by? Seems like I'm off by just 1. But perhaps this should be 5 and this should be 3. That seems a little backwards. And then we have to decrement. See where that gets us. Make sure to compile on the main program. Spin her up, MR under the report. There's a breakpoint. Next string. So wait. I have this backwards. So these two are the return values, return address. This is the value we passed, and this is the value we passed, and this is the return address to the function itself, the above function. So really I've got these backwards. This is supposed to be 2, and this is supposed to be 4. So I pushed value then string, right? So look at the way we pushed them. Right. We pushed the command string, and we pushed the dump start. See that? So, all right, we're gonna copy the stack pointer, get it to 9. That is that plus 2. Ah, right, because it's at the next location. It's not pointing to the last value. It's at the next location. So yeah, little minor detail. So that should be 3 and 4. Let me get rid of that. 3 and 5. Build, run some more. So there. Now we finally got the correct data register to point to the values that we pushed on the stack. So the string value is this location. Actually, it isn't. That isn't the string value location. That's the destination value location. Again, had these right the first time, except backwards. 5 and 3. All right. There we go. And again, compile on the actual program. All right. There we go. The string is located at 0003. So now we want to load that string location. So we're going to load the LSB into A. And really, that's the MSB. And then LSB into B. And it should be B, L, A. Yes. Lots of one or the other possibilities. There. We have our address, and it's correct. Load must be into A, which is 0, and so it's boring because you can't see anything change. And we're going to decrement the stack pointer, and I did that wrong again. Increment versus decrement. What do you know? Had that right the first time through. So we're looking at the right spot. I load that 0 into A, which is boring. You can't see it change. All right, increment it to the 3. We load the 3 into B, which we can see change. Now we're going to load B into R and load A. You'd think by now I'd know the order of these things. This literally, all of these commands are load, destination, source, right? So we already loaded into B. We need to load R with B. We need to load D with A. Compile. Run. There. That gives us the value, FFC. All right, load our 0 into A. No biggie. Increment. Load our 3 into B. Bonus. All right, now load R with B and load D with A. And now we have our data pointer pointing to the location that we passed on the stack. Yay! Such simple successes. All right, and then we have that halt just to make sure that we got everything lined up right. All right, so I'm going to be done with this for the moment. So now that we've done all that to make sure we have our pointer, now we want to load that character from our string into B, and then we can check whether it's a hex digit or not. So first load the value into B. It's pretty much load B from memory. That's pretty much what I'm going to do. And that's going to be load B from memory based off of the stack pointer. So here's load B from memory based off of the DR register. So that gets the, well, actually the third character of the string. And then we can call the util function. It's just above this, which is hex digit B. So now we've called is hex digit B, is make sure that that's a hex digit, 0 to 1, A through F, capitalized. Which might also make it worth doing a do to upper in the string, but we'll deal with it. So now we got is hex digit B. If it is a hex digit, and A is going to be something other than 0. So let's see. See what's the thing here. So we put in a character 0 through 9, A through F into B. We call this function. If it is in that range, then A gets to set 1 if it's a value, and then B should actually be the value of the digit itself. So So now we have B has the digit itself, and A is whether or not it is a digit. So first, let's check if it's a digit, and we can do that by comparing A to 1, right? So we can load A with 1, which is LAO for 1. Then we can make T, which is, let's just go ahead and comment as we go. We'll just make it as abbreviated C. So A equals 1. A equals A. Oh, not that I wanted to. LTO. And LTO is down here in the reds. That's load A with 0 with 1, B with 1, T with 1, 0, 0, 0, or FFF. That's our built-in values. So we want to make the temporary register 1, A equals A minus T. And that'll destroy the value of A, but then we can say jump short, if not 0, it isn't a digit. So what do we want to do? What's the plan on this one? And let's just jump out early. Leave whatever's converted, and jump out early. What's the harm? So we want to jump to xtos.return, which doesn't exist yet, but that's okay, because we can make it here. Define xtos.ret. So I guess the symbols with a dot in them are sort of meant to be local symbols, but I don't really have a concept of local symbols. That makes them, by having a period in them, they don't get reported in the symbol table, because they are meant to be internal, if you will. They are global, though. You can't define another xtos.return somewhere else. All right. Same thing with these. Once they're defined, they're global, but hence the concept of sort of using the decimal to make it part of the larger thing. All right, don't need to halt. All right, so says A was not equal to 1. So it is not a valid hex digit. So we're just going to exit out. You know, we can give you all sorts of warnings, but that's for the higher level languages. All right. So if it is a hex digit, B should contain the value converted from character to value. So now that B has our value, what we want to do is store that value in the destination's location, which is P value, right? So to do that, we need to poextos.val, and we're reading big Indian and writing little Indian. So we will increment the DR pointer to get to the little Indian, or the big Indian byte, the MSB. Now, we have it in B. To bring the MSB in, actually at this stage we can just write the MSB. But because this is the upper nibble of the upper byte, we should take the value, shift it left, and then store it. We'll shift left 4 to be exact. And shift left 4 is, where's that command? Shift, shift, shift. Oh, there's an alarm. Be back in a bit. Mute. Mute off. That's good. Oh, I lost the viewer. Oh, darn. Let's see. Can you hear me now? Somebody say something if you can hear me. Or not. All right, where were we? Let's see. We load the string value. We increment the data pointer because we're looking at the most significant byte. Now we need to adjust that byte because it's only the upper nibble, so it needs to be shifted left 4. And look at the gory details. Yeah, shift left. Shift left are the orange. Shift left A, B, T, and D. All right, so shift left, which is TLB. So shift left B once, twice, 3 times, 4 times the lady. Yes, I know it'd be nice if it were more than one command. Or I could shift left more than once in each command, but that does each one. So it's got it all shifted. Now we need to store B at the location. I guess I could probably, just for convenience, let's do this. And we'll make a comment. B contains the numerical value of the character. So if it's 0, it's 0. If it's 1, it's 1. If it looks like a 2, it's a 2. Character for the upper nibble of the MSB. 4 shifts to move it to the upper nibble. And we load the destination, we get to the upper byte of that destination, and now we're going to SCV, which is store using the stack offset, not the stack. Here it is. Store indirectly B. That's what it is. Indirectly meaning the data register. Segment, we start. Now, this is where the fun begins. Now we want to get our pointer back to the string again. Right. So now we need to look at the 4th character. So we're looking at the 3rd, the 4th, the 5th, and the 6th characters. This was to load the 3rd character. So now we need to load that. Oh, messed that up, didn't I? Nearly. All this does is load the address that I'm looking at. And I need to do this. collection, which is to dereference the pointer on the stack to the address of in RAM that we're actually looking for. Now our DR register has the first location. Then we can increment it to get to the most significant byte. Then we can store. Well, that looks confusing as hell, doesn't it? Well, nobody's confused because nobody's talking, so that's good. All right. Now we store the B value. And we need to basically do the same thing over with the next value in the string. So do all this. That loads us up with our string value once again. That was the third value from the string. We need the fourth value from the string. So we will increment the DR pointer. We will then get the fourth character. Do this again. Fourth character. See if that's a hex digit as well. If it's not, we cut out early, leaving what other garbage is left behind. So now we need to store it, but it's already the lower one. So now, all right. So now I'll be containing the numerical value of the character for the lower nibble of the MSB. We don't need to shift it. Dereference the pointer. Now we need to, let's see, that's in B already. So let's load it into A. Oh no, I'm destroying my B, am I? Dang it, Bobby. Am I destroying my B? Yeah, I'm overwriting B. Let's get it shifted. So let's oh wow. This is gonna trash T. So instead of loading into B, let's load into T. Use T instead. Yeah, because otherwise I'll destroy the B value. Okay, capitalizing. All right. So now we've stored the value. We can use B again here. Get the fourth character of the string. Let's do the same thing here. T. Alright, so I don't destroy my B value. B is a special purpose register. So, alright. Character for the lower nibble. Alright, so we've got all that. We need to go to increment to get to the upper nibble. Now I need to take the value that we saved back out and put it somewhere. Let's say T. Let's load T indirectly. Load T from memory, rather, is what I should say. Now we have the previous value of T that was stored off is now read back. And we've got our lower nibble. And because I know our upper nibble and our lower nibble are separate from each other, I should just be able to add them together. Should be able to just add T to B. So let's see the sum of B, T. So let's see, continue our C. dr plus plus. This goes T equals dr dereferenced. I guess it should just be this. Dereference dr is a byte. And this is B plus T. Alright. dr should still be in the right place to store it back now. So I should be able to store directly B. That should be our upper level. For full byte. Now that's going to be all of that to convert two text digits to a numerical value. Let's see how she runs. That ought to be fun. Save that. Build that. Builds nice. Let's run that. Run MR 1, 2, 3, 4. All right. So get comfy. So we have XTOS string. So this plus 5, right? It's located here. String. With R with that, well that, all right. So now we've got our pointer to our string, which is MR1234, and it's pointing at the 1. So here we move that into B. I'm going to call is hex digit B. Unfortunately, I don't have a step over function, so we're going to step into this. Value is not a hex digit. Oh, geez. How did this mess up? How did is hex digit B not work? Thought I tested that already. We're going to jump out there, and then we're going to return, and it's going to be a nothing. And we're going to dump lines, and it's still 0, 0. All right. I thought I had that. Is digit test. Hmm. Let's see what this program runs as. Compiles properly. What this should only do is allow for hexadecimal digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Nothing else. No lower cases. Right. All right. Let's check out his hex digit, which was just above this. Check if the input is greater than slash. Right below the at sign, because at is above A. It's digit B. Oh, it only checks if it's A through G. This checks if it's a digit. So is digit test was get hex line. All right. So if you check if it is a hex digit, and then Or do I want to change hex digit B? This digit checks if it's 0 to 1 or 0 to 9. And his hex digit checks is through F. Should I combine these? Don't know. All right, well, if either of my two watchers have any ideas, what do you think? Should I call the two functions separately, or should I combine them? That's kind of what I thought the goal of is hex digit B. I think I want to include it here. Value is not a digit, so set A to 0 and returns it being Should I combine them or not? Because that's kind of what I wanted this to be. It's check if it's numeric or not. I suppose. This is the first thing we can do. Is check if it is. What we could do is call is digit B. And then yeah, it is digit B. Digit B says the same thing. Sets A210 to indicate if either is not a digit. So let's just say, let's say essentially if A equals 1, we already have our value and we can return. Essentially. So now I want to load T1. Sum or subtract from A. Either way, A from T or T from A, right? It's going to either be 1 or 0 or -1. So we subtract them. Then we're going to jump short if not equal. To num check, say, versus letter check. So this essentially is, I'll call that letter check. And then otherwise, return. All right, so did that work? I'm going to go to is hex digit, which means it calls is digit. Is digit comes back with a 1 in A. Compare that to T being a 1. And short if it is not 0. So if I'm doing this right, so we get in there a number comes in, we go to that, it is a number, A is 1, we load T with 1, we subtract the 2, that should be a 0. If it was an actual 1, then if it's not, then we're going to jump to the letter check. Otherwise, we're going to return, and B should contain the converted value from his digit B. And if I do an MTA, we leave the value of A alone. So this is T equal T minus A. I type in today. All right. So is X digit B called is digit B. If our A is 1, we return. And we leave A unmolested and B unmolested. And we just return. Otherwise, B is still the questionable value. Right. All right. Cool beans. Now let's see. Everything compiles nicely. Always a good sign. All right. So let's take value. We take that value over there and then add 5. That points us to here, which is the MSB of the address to the string. So we're going to put that into A. This is 0. Super not interesting. Increment that. And we're going to take 3 and put it into B. All right. And we're going to take these, move them over to DR. Now dr points to the location, and sure enough, it's the first character, the 1. Load that into B. Call is hex digit B, which is call is digit B. Right. Load to left, subtract, down, load that value, subtract, and down, use the 1, subtract the that doesn't look quite right, does it? No, that doesn't seem to be doing the trick right. That's not supposed to be 32. It's supposed to be 1, the number 1. Ah, come on. So something not quite right there. So let's just escape and start over, because is digit B. So it's minus B T loop T 30. That should have converted it. Let's try again. Run that. 1, 2, 3, 4. Right. 3. Here we are. Oh, it's not 31. It's 32. This is 0, 1, 2, not the third digit, the second digit. Offset. But anyway, we're looking at 32. Isn't quite what we're supposed to be looking at, but whatever. Well, 32 is a valid numeric digit. 32 is in B, so is it a hex digit? Is it a digit? Load. I hate when that happens. Load to F. Track that as FD. So it's not within that range. Flag is not set. So load A with 0. B is 32. T is 30. Minus B and T. What in the flurp? What in the flurp? Minus BT, right? That's my instruction, right? Minus BT, yeah. There it is. Hmm. Why is that not working? Let's do that. So instead, we're going to use A and B instead of T. And I need to find out why subtraction with T ain't right. I have to figure out what that is. Okay, so why does my T subtractions not work? Anyway, that works. There, now it's 2. Okay. Now 1 into A, indicate success. Return, check if it's an A. Success. This is because it keeps jumping back and forth. There we go. Why is it not recovering? Well, that worked. Why is it B and T subtraction not working? That is an odd problem to have. There. Now we got the 2, and we want to shift left. There's the 4, and an 8, and a 2, and a 2. So now we've got our 2 shifted left. We get our location. I there's A, B, C, D. That's our destination. We're going to store our tool right there. All right. Now we're cooking with gas. Now we're going to load up the location of the string again. Right. And then move it on to the next one, which is 33. So instead of 1, 2, 3, 4, it's 2, 3. That's what we're converting. Hate when it does that. All right. All right. So that worked. Now we're going to get the value from MSB. I swear. There we go. All right, now we want to increment that. There's the 2 that we stored earlier. Now we want to store the 3. So we're going to load that 2 into T. And then we're going to add B and T together. That gives us the 23. Now we're going to store that back out. Bonus. We're mostly working. All right. A couple of corrections here. And we go to edit. We only need to do 2, not 3 there. All right. So it should work for the first 2. And it'll give us a different location anyway. So save, build, run the program, MR1234. So this should dump out. Let's just run from there. Yeah, there we go. So it started at 12. Hadn't done the other part of the address, but that's progress. A little less progress that it rebooted afterwards. That's probably because we're not telling it to do anything. Let's see. Yeah, after we get through all this, we return. And we go off into the weeds because when we return, let's see, memory function. We loaded dump start, right? Stored those. Or rather, we stored command string and dump start on the stack. Then we made the call. We need to do stack +4 to clear up the stack. So the increment stack. So that should have us corrected so that we return to the proper place. All right, build, run more, MR, let's try 2, 3, 4, 5. Just let run. Yep. 230, and notice we didn't do the boot banner, so we didn't reboot. Got to clean up your stack. Nobody knows what that means. Let's see, MR 22. That's not interesting. 2545. All right. Well, that's good for now. We'll finish up the 4-5 and come back to it later. Well, if you were hanging out at all, thanks for hanging out with me. We'll do some more of this later, maybe. And we'll talk to y'all later. Bye. Okay. Oh, it's all confused. No telling where it's at. Okay. All right. Let's stop the camera there.